So, that main tool of attack is so what is the goal, right? Goal is to you want to find PM for the Jackson network, right. So, the main tool is going to be a guesswork theorem. Okay. The guesswork theorem in particular, it is the guesswork theorem 7.6.2 in your book, which we studied. If you manage to guess the reverse transition rates which satisfies Qij is equal to Pj Qji star, then you can guess the steady state probabilities Pis, right, and that is the correct answer is what your theorem 7.6.2 said. All right. So, we will use this technique. Okay, the hypothesis or the guesswork, right. The time reversed CTMC of the Jackson network is another but different Jackson network. Okay. This is the hypothesis. I am going to guess some transition rates for the reverse Jackson network. Okay. First, let me develop some. So, let me first put down some notation. So, this is all this lambda naught is the exonode arrival rate. So, let me denote. So, denote by lambda I as the total rate of customer arrival to node I. Okay. Which is, see, lambda I is not the same as Ri. Okay, Ri is the rate of exogenous arrivals to node I. All right. The total rate of customer arrival to node I will be Ri plus all the rates of traffic, all the traffic that is coming from other nodes to node I. All right, because you can complete service in node j and come to node I also, right. So, this lambda I will be equal to Ri plus sum over all the traffic leaving node j, right. So, the traffic that is entering node j, the total rate at which traffic enters node j is also the rate at which it is leaving node j, assuming that everything is stable. Of course, we have to assume here that assume lambda. So, lambda is the total arrival to node I. So, assume lambda I less than mu I, right. Without that, you will not have even the stability of the node I. So, this is true for all I equals 1 2 dot k. Then you will have Qji, right. So, this is the rate at which traffic comes into node I. I can write this as lambda naught Q0 I plus sum over j equals 1 to k lambda j Qj I, right. So, in effect, what is lambda I? The total, the lambda I satisfy the following equation. They satisfy sum over j is equal to 0 to k. So, I am just including node 0 also in this sum, lambda j Qji. Correct. So, lambda I, which is the total arrival rate at node I, satisfies this. See, this lambda I, the arrival process at Qi may not be a Poisson process. Okay, this lambda I is the rate of the arrivals, but the arrival process may not be a Poisson process. Why? Because if you have, in cases where there is feedback, right? We even saw with the one queue with the feedback, the arrival process seen by the queue can be quite bursty. It need not be a Poisson process. If you have an exclusively feed forward Jackson network like tandem queues, or you get out of a tandem queue, split, feed forward into more queues and go out altogether without any feedback whatsoever, then you will have Poisson inputs to all the queues. But the moment you have some feedback, some cycle back into the same queue or some such thing, you may not have a Poisson process of arrivals to each queue. So what's the bottom line? So a Jackson network, the arrival process seen by a queue at the Jackson, a single queue in a Jackson network may not be a Poisson process. It has some rate lambda I, okay, but this process lambda I may not be Poisson. If there is no feedback, if the entire Jackson network is feed forward, then it will be a Poisson process. Okay, but what's interesting is that even though this lambda I arrival process is not a Poisson process, each queue will behave as though it's an MM1 queue. That's what we are going to say. We are going to say eventually. Okay, at any given time t, if you take a photograph of the system at time t, the occupancy distribution looks like there are independent MM1 queues. Okay, that's what we are. That's where we are heading. Okay, good. So this is the equation satisfied by the lambda i's. All right. Now this Qij, so this is a this Qij's or Qj's or whatever they are, it's a stochastic matrix, right. So this Qij, if you look at Ij in 0, 1, 2 dot 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 k, this forms a stochastic matrix. Okay, so if you have, if it's irreducible, right, assume that this is an irreducible stochastic matrix, right. Okay, if you assume an irreducible stochastic matrix of this Qij's, which are the routing probabilities, then this system of equations, right, this when you run this over I equals 1, 2 dot 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 k, when you run this over, so when you run this lambda I over all this k, this system has a solution. Okay, if you assume an irreducible Qij, this system has a solution. Which is unique up to a normalization. Now see, you can view these lambda i's are as at some level, it's like the pi i's, all right. It's like the pi I system for, if you think of some DTMC with these transition probabilities Qij's, and it's an irreducible DTMC, it will have some pi I, right, and this pi I is in a DTMC is normalized to 1. Here the lambda i's are not normalized to 1. Okay, these lambda i's are determined. The only thing that we know in this lambda is that lambda 0 is known, right. So once lambda 0 is known and fixed, this is a unique solution to the system of equations. Okay. Lambda I is unique. This solution lambda is unique. Okay, so that system of equations has a unique solution. Okay, that's just determined by solving the steady state vector of the stochastic matrix Qij. All right. Now guesswork. Okay, so this is all set up. So I just define lambda is as the total arrival rate and node I. I said that it satisfies this this balance equations, which has a solution. The solution is unique if you fix lambda naught, which is the exogenous arrival rate. All right. Now guesswork. The guesswork is guided by our hypothesis, which we have not yet shown, right, but we will show it. The hypothesis is that the time reverse CTMC of the Jackson network is another Jackson network. Okay. The guesswork is that it's the reverse process is another Jackson network, and I have to specify all the the arrival rates. What's the Jackson network specified by, right? It's specified by the exogenous arrival rates, the server rates, and the transition probabilities, right? Now, what would you guess, right? Exogenous arrival rates for the reverse. So, for the for the reverse Jackson network, I don't know already that it's a reverse Jackson network, but I'm going to hypothesize this and propose some exogenous arrival rates, service rates, and transition probabilities, or the the routing probabilities. Exogenous arrival rates are I'm going to say are lambda naught q0 j star, okay, for node j. Number 2, routing probabilities qij star to be determined. In reverse time. 3, the same exponential mu j service at node j, all right. So, for the reverse Jackson network, I am proposing these as this is the arrival rate, service rate, and routing probabilities, where I am going to say that qij star, I want it to satisfy, this is what I want, right, lambda i qij, which is the rate at which traffic goes from node I to node j, right. I want it to be the rate at which traffic goes from node j to node I in reverse time, right. The total arrival rate and the total departure rate of node j is still lambda j in both forward time and reverse time, and I want the reverse transition probability qj I star to satisfy this equation. Okay, this is I want this for both node 0. So, I am also defining q0 j here, all right. I j less than or equal to k, right. So, I am going to have qj I star equal to lambda I over lambda j qij for 0 less than or equal to I comma j less than or equal to k. So, this is how I am going to propose the reverse routing probabilities. Okay. So, this is some Jackson network, all right. So, I have just come up with exogenous arrival rates of whatever, service rates of mu j, and routing probabilities of qij star, which is like so. Now, I want to show that this is in fact satisfying the guesswork theorem's conditions. Okay, the guesswork theorem of 7.6.2 or whatever we studied earlier, right. So, backward transition rates. So, what will the backward transition rates be? So, this is the proposal for the backward Jackson network. So, the backward transition rates will be, let us call them q star, okay, m comma m prime between any two states, okay, will be lambda naught. It's almost similar to the forward one, except you have the stars, all right. For m star m prime is equal to m plus ej equal to mu I q I 0 star for m prime equals m minus ei for mi greater than 0 and equal to mu I qij star for m prime equal to m minus ei plus ej for mi greater than 0. Okay. This is true for 0 less than or equal to I less than or equal to k, 0 less than or equal to I less than or equal to k. Equal to 0 otherwise. So, this is the backward transition rates. Okay. What I am going to do is substitute this guy into this guy. Then what happens? If you just blindly substitute that into this, you get, you can just do this is just an algebraic exercise. You get q star, the reverse transition rates, m prime equals lambda j q j 0 for m prime is equal to m plus e j is equal to mu I q I 0 star, right. Q I 0 star, I can write it in terms of q 0 I, which is mu I what is q I 0 star? So, I am going to use that equation, right. I am going to use that equation. So, I will get mu I lambda 0 by lambda I q 0 I, okay, for m prime. So, this is just a substitution, okay. M prime is equal to m minus e I for m I greater than 0, 1 less than or equal to I less than or equal to k. This is just a blind substitution, and finally mu I q I j star will be q j I lambda j by lambda I q j I, right, for m prime is equal to m minus e I plus e j, where m I greater than 0 and 1 less than or equal to I comma j less than or equal to k. Also, it is I comma j, all right, equal to 0 otherwise. So, what have I written, right? I have written out the reverse transition rates in terms of the parameters of my original Jackson network. See, here I had the Qij stars, which are the reverse transition probabilities, but I am enforcing some kind of reversibility by using this equation, right. I am not enforcing reversibility, I am just looking at what the reverse transition probability should be, right. It is not reversible, of course, I made a mistake in saying that. So, you get qm m prime star in terms of the parameters of your original Jackson networks, all right. So, this is what I got, right. Now, I want to verify what? Two things, right. One thing I want to verify is, or want to verify meaning what, want to, so guesswork, so I should do guesswork, right. I have done guesswork for the backward transition rates. I have to do guesswork for want to guess PM, right, to satisfy two things for the guesswork theorem. One is I want it to satisfy Pm Qm m prime equal to Pm prime Q star m prime comma m, right, where Q stars are the proposed reverse transition rates here, right. Q stars are given by that set of equations. And second, I should also guess that, I should also satisfy that sum over Qm m prime sum over all m, right, should be equal to sum over Q star m prime when you sum over all uh, so I think there may be a small mistake here. Let me just verify this. Yeah, so I want to verify sum over Q. Yeah, so it should be m over m prime. Okay, Q star m prime. Okay, so that's what it is. So these are these are demanded by so these are demanded the guesswork theorem 7.6.2. If I do manage to verify these, then I can immediately assert that Q star that I have above are in fact the reverse transition rates of the reverse Jackson network, and that Pm is in fact the steady state probabilities of the Jackson network of both forward and reverse Jackson network. Okay. So, I have to verify these two equations, right. Somehow I have to find Pm to satisfy these two equations. I already have a proposal for Q star. So, I want to have a proposal for Pm, right. So, if you look at this, so how do I go about calculating Pm is the question now. Okay. So, if I just look at this equation, right. So, that I am just rewriting this first equation, Pm is equal to, sorry, Pm times Qm m prime. So, this is what I want to enforce, is equal to Pm prime times Q star of Q star m prime m, right. Now, I can write down, so Qm m prime I already know from here, right. So, this I already know, so that is tick, and then I know Q star from here, right. So, if I just plug that Q and Q prime, sorry, Q star from those two equations above, what I get is that I will get P of, so Pm times rho j equals P of m prime for m prime equals m plus Ej. I will get P of m is equal to P m prime times rho I for m prime equals m minus Ei, and I will get finally P m times rho j equals P m prime times rho I for m prime is equal to m minus Ei plus Ej. Okay. Here rho I is equal to just lambda I over mu I, which is less than 1. Okay. So, rho I is the load on the ith node, it is the total arrival rate by total service rate. So, this is what I get, this is just algebra. Okay. You have this equation 1 which I want to enforce by the, for the guesswork theorem to hold. I know Qm prime and Q star mm prime proposal I already have, and I just plug it in, I get that stuff, all right. Now, from here it is quite easy. Okay. So, what are we looking at? So, if you look at P m prime and look at P m, where the there is an entry that is decreasing by 1 in the ith position, I have to multiply by rho I, right, and likewise if the jth entry is increasing by 1, I have to divide by rho j, right, and if 1 is decreasing by the ith position is decreasing by 1 and the jth position is increasing by 1, then I have to multiply by rho I and divide by rho j, right. So, you can start at some state. So, if you are looking at a state P m which is equal to P, let us say m 1 0 0 0, I can get this by just starting at P 0 0 0 all 0 state and then multiplying by rho I, sorry, rho 1 power m 1, right, that is because of the above equation, right. So, this is one kind of an m. So, I can just put out, I can just do it again and again, right. I can just, so if I have a state which is just P m, which is P m 1 m 2 dot 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 m k, I can just obtain it as P 0 0 0 rho 1 power m 1 rho 2 power m 2 dot 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 times rho k power m k. Okay. I can keep iteratively doing this and get this, right. So, I just need to find P 0 0 0 which I can do by normalization, right, which is obtained by sum over P m, all the states m has to be equal to 1, which means that P 0 0 comes out and then I have sum over m 1 rho 1 to the m 1, sum over rho 2 to the m 2, sum over m k rho 2 to the m k, right, which means that I can just sum all these geometric series, right, since all these rows are less than 1, P 0 0 0 will turn out to be just 1 minus rho 1 times 1 minus rho 2 dot 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 1 minus rho k, from which I can get P of m, which is P of m 1 m k is equal to product I is equal to 1 to k 1 minus rho I to the m I. Okay. So, this is the PM that I obtained by enforcing this this guesswork theorems condition, which is PM m prime, I am talking about this equation PM times QM m prime is equal to PM prime times Q star m prime m, right, where Q star I have already guessed. So, if I enforce this is the PM I get, right, and of course, so this PM that I have worked out satisfies that equation, right, because I have enforced it, right. Then the other thing to verify is that sum over Q m m prime is equal to sum over Q star m m prime, right. This is just an algebraic exercise, because I have a proposal for both Q m m prime and Q star m m prime. So, Q m m prime I already know and Q star m m prime I have a proposal, and this I can just verify by algebra. Okay, it works out to be correct. Okay. So, I have verified. So, what I have done is that I found a PM which satisfies equation 1 and I found PM and Q star which satisfy equation 1 and equation 2, right. And since all the mu's are bounded, the technical condition sum over Pj nu j is finite is also satisfied. Okay. So, by guesswork theorem, so this is this so this PM satisfies 1, right, then 2 which is easily verified to be satisfied. Just algebra, I by 2 I mean so that equation, right, that guy. Okay. So, this means that guesswork theorem can be used by guesswork theorem. (7.6.2) in Gallagher's book, PM equal to all that, right, pi over I is equal to 1 to k 1 minus rho I to the mi is the steady state probability of the CTMC corresponding to the Jackson network. And of course, QMM prime star correspond to the reverse transition rates. Okay, so our guesswork for the QJI stars are in fact correct. Okay, the system is positive recurrent, and you have found out the transition rates for the reverse process and the steady state probabilities. Okay, so this is excellent, right? So this is so what's remarkable about Jackson network is that the steady state probability looks as though it's an MM1Q with load rho I, right? So this is a product form of k MM1Qs, right? 1 minus rho I times rho I to the mi. It looks as though, so the steady state probability of the Jackson network looks as though it's a product of independent MM1Qs, although they are not at all independent MM1Qs, right? See, it's not at all the case that the Qs are independent, right? So if you look at Q1 at time 1 and Q2 at time 1.5, Q2 at time 1.5, they will not be independent, they will be dependent actually, because there is all this traffic growing between them. But at any given time, in steady state they look like MM1Qs. This is in spite of the fact that they are dependent Qs, and very importantly, the arrival process at any given Q need not be a Poisson process, as we argued, right. The lambda I arrival process, the aggregate arrival process at Qi is not Poisson in general, it is Poisson only for feed forward networks. So, the moment you have some cycling back, you will not have Poisson, but it still looks like an MM1Q with load rho I. Okay, it looks as though it's an MM1Q with arrival rate lambda I and service rate mu I. Although the arrival is not Poisson and the queues are not independent, the queuing processes are not independent, but the steady state corresponds to this product form. Okay, so this is very nice. This is very easy, very nice way of analyzing these complicated interconnected queuing systems. All right, using Jackson networks. So what we have made heavy use of is this guesswork theorem, right? The guesswork theorem turned out to be very powerful. In fact, using this guesswork theorem, you can study even more complicated networks. For example, you can have state dependent service rates, right? We have assumed mu I is constant for that server, right? But you can have server number 3 which serves at different rates whenever there are different number of customers, right? All that is allowed. Okay, and not much will change. Okay, in fact, there's a book by Frank Kelly which deals with these reversible and product form networks in great detail. Okay, but the crux of the argument is just like this, so you can just understand in one lecture, but there's actually an entire book worth of material on these sort of product form networks by Frank Kelly, which is a very nice book. So I'll stop here. So that concludes our discussion on Markov processes, continuous time Markov processes. We will just have a discussion on semi Markov processes, and then we will complete the course. Thank you.